Bismillahirrahmanirrahim. Hello dear students, I hope you are all fine. I welcome you all in class of Real Analysis 2. Our discussion is continue on functions of bounded variations. In the last lecture, I discussed first theorem related to bounded variation. In today's lecture, I will discuss a second theorem related to bounded variation. Statement of the theorem says that f is a function from closed interval ab to r. This shows that f is a real valued function over the closed interval ab. This function is a monotonic function on closed interval ab. Show that f is a function of bounded variation. Theorem says that if a function f is a monotonic function, then it will always a function of bounded variation. Firstly, we discuss what do you mean by the monotonic function. We know that a function f is called monotonic function if it is one of the type. A function f is called monotonic function if it is either increasing function, it is either decreasing function, non-increasing function, and the fourth type is non-decreasing function. So if your function is one of the type, then we say that this is a monotonic function. In some context, increasing and decreasing functions are also called strictly increasing and strictly decreasing. Further, a function f is called increasing function if for every two numbers x1 and x2 belong to the domain of f, if x1 is greater than x2, then f of x1 is greater than f of x2. That is the for if x1 is larger than x2, then the value of f, that is the image at a larger number or larger pre-image is greater than the smaller image, then such function f is called increasing function. Similarly, if x1 is greater than x2 but your f of x1 is less than f of x2, in this case we called f is decreasing function. And for non-increasing and non-decreasing, the difference is only that for non-decreasing means your function f is increasing plus constant. So for non-decreasing case, here there will be a equal sign, and for a non-increasing means your function is decreasing plus constant function. So if your function f is monotonic function, that is your function f is one of the type, then we need to show that your function f is a bounded function, function of bounded variation. Further, in the previous lecture, we have discussed what is the definition of function of bounded variation. A function f is called function of bounded variation if its total variation is finite, and the total variation will be finite if the sum of total variation is bounded or its supremum exists in a real line R. Further we discuss here. Okay, as we know that f is called function of bounded variation over the closed interval ab if the total variation of f, that is, this is the formula, this is the definition of total variation. Total variation of f over the closed interval ab, here I am represented this as va to be f, supremum of this sum. This sum is called sum of total variation. So this is the definition of total variation. If this total variation is finite, then f is called function of bounded variation. Further, this total variation will be finite if this sum of variation is bounded. So this is possible when sum of total variation is bounded. Case number 1. Suppose that f is monotonically increasing function. As I have discussed here, f is monotonic. So monotonic function is one of the type. Either it is increasing or decreasing. So let f is monotonically increasing function. This is our first case. Since f is increasing function, so when xi is greater than xj, xi and xj are the two numbers belong to the closed interval ab. And these two numbers, values of f, that is f of xi, will be greater than f of xj. Now consider the total variation k is equal to 1 to n f of xk minus f of xk minus 1 for the partition p a is equal to x naught, x1, x2 up to so on xn equal to b of the closed interval ab, where the numbers are in this order: x naught is less than x1, x1 is less than x2 up to so on less than xn. So by this sum can be open as f of x1 minus f of x naught. By putting k is equal to 1 here, this will become f of x1, this will become f of x0, plus by putting k is equal to 2 here, this will become f of x2 minus f of x1. By putting k is equal to 3 here, this will be f of x3 minus f of x2 up to so on. By putting the last number k is equal to n here, this will become f of xn minus f of xn minus 1. So this is the expanded form of this sum, and this sum is actually total sum of total variation. So next our target is to show that this sum is bounded. As in the last expression, here there is an absolute sign over this difference. Every difference have absolute sign. But we know that a minus b absolute is equal to a minus b if a is greater than b, and a minus b absolute is equal to minus a minus b if a is less than b. So in our case here, because our f is increasing function, so when we choose the two numbers x0 and x1, as we have supposed that our partition points of our partitions are in this order: x0 is less than x1, this implies f of x0 will be less than equal to f of x1 due to monotonicity of the function, because here we assume that our function f is increasing function. That's why here f of x0 will be less than f of x1. When f of x0 is less than f of x1, this implies f of x1 minus f of x0 will be greater than 0, or in other words, f of x1 is greater than f of x0. So the absolute difference of this number is only equal to f of x1 minus f of x0, because we know that x absolute is equal to positive x if the quantity inside the absolute is greater than equal to 0. So here the quantity inside the absolute is f of x1 minus f of xn, it is positive. That's why this absolute can be written as without absolute lines. Similarly, for the other terms of the sum of total variation, f of x2 minus f of x1 absolute is equal to f of x2 minus f of x1 up to so on f of xn minus f of xn minus 1 absolute is also equal to simply f of xn minus f of xn minus 1. So that's why we are now taking here absolute values. Now, as you can see that here the terms are such that f of x1 has a positive sign here and f of x1 has a negative sign here. So the terms are in alternating signs. So all the terms will be cancelled except the two terms. First term is f of x naught. This is only one time, and also this last term f of x1. These two terms are only occur in this summation one time, whereas every other term will occur in this summation two times. One time with positive sign and one time is a negative sign. So by cancelling out f of x1 with f of x1, f of x2 with f of x2, up to soon we have only two remaining terms, f of xn minus f of x naught. As x naught is the first term of the partition, that was A, and xn is the last point of the partition, that was B. So this can be written as f of B minus f of A. So this sum of total variation is bounded because f of B minus f of A is a finite real number. That's why our sum in this case is bounded. Similarly, when we consider f as a monotonically decreasing function, then sum of total variation will be equal to f of A minus f of B. The just difference is that in this case, the sum of total variation is f of B minus f of A, whereas in this case, the sum is f of A minus f of B. But f of A minus f of B or f of B minus f of A, both are the finite real number. So in both cases, our function, our sum of total variation is bounded. So our function f is a bounded function. So we have proved that if your f is monotonic function at some closed interval ab, then your function f is function of bounded variation. I hope today's lecture was helpful for you. Inshallah, we will discuss a new theorem in the next lecture. Take care. Allah Hafiz.